So we left off looking at the pin arrangement for the PIC 18F458, the 40 pin configuration. Again, as we said, the PIC that we're going to be primarily interested and focus on is the PIC F4520. And it's a good idea to look at the spec sheets on the 4520 so that you have an idea of what the spec sheet says as we're going through the text for the PIC 18. So we can take a look at the tri-state register, the role in outputting here, and we can see that the I/O port pins and their functions for each of the ports A, B, C, D, and E, latches A, B, C, D, and E, and the tri-state buffers A, B, C, D, and E. And we can see the address notation for each of those ports as it applies to the location in the PIC 18. So you get used to seeing these addresses, especially if you started getting used to using the MP Lab. You need to be familiar with these addresses, because as you go through the watch windows, you can see what's going on in each of these ports as they're configured by knowing the address location. So each of the ports, A through E, as depicted here, can be used for input or output. The tri-state special function registers is used solely for the purpose of making a given port an input or an output. So you have to define those. For example, to make a port an output, to write zeros to any tri-state buffer, X register. In other words, to output data to any of the pins of the port B, we must first put zeros into the tri-state buffer register to make it an output port, and then send data to the port B special function register. So you need to keep that in mind as you're going through the exercises. If you start having problems with data not being present, well, maybe you did not clear the register first by putting the zeros there and then placing the information that you are interested in. Okay, so in this case here, you can see that each of the ports identified here identify port B, tri-state buffer B, that has to be done in order to make the register function as you desire. If you don't set it up and don't do it correctly, it's going to do what you want exactly wrong. So if we take a look at the following code, it's a good idea as you were going through these, whenever you see code, open up MP Lab and enter the code in and see if it actually does what your textbook says it's going to do. So in this case, it'll toggle all 8 bits of port B forever with some time delay in between the on and off states. So you should be becoming familiar with these simple commands: move literal to the working register, move the working register to some file, move the literal to the working register, move the working register amount to some file. So you can see in this case we're moving information to the working register to the tri-state buffer, from the working register to the port B. And then at this point they're calling a delay. So you've got a delay there to slow things down, because typically what happens as you're observing things and seeing things as the processors are working through it, it's typically too fast for you to see it. You will never see it unless you stop the program or you introduce a delay in there to slow down the process. So the next step, again, you're going to move a literal value to the working register. The working register will now have AAH in it, and then move the working register value F, in this case F is port B, put AAH on the port B pins. Okay, let's correct that. And then call another delay and then go to L1. Well, what does L1 do? It tells you to jump back to this step and do it again. Jump back to this step and do it again. One of the things you'll notice on this particular little example is there's no end. There's nothing in here to keep this thing running forever. And as it said in the beginning, it will continue to do it forever. So it must be noted that unless you activate a tri-state bit set to 0, the data will go on from the port register to the pins of the PIC. This means that if we remove the first two lines of the above code, the 55H and the AAH in hex, those values will not get to the pins. They will be sitting in the special function register of port B inside of the CPU. To see the role of the tri-state buffer registers then in allowing data to move from a particular port to the pins, we can take a look at these examples here. A typical example of a circuit symbol in Appendix C of your textbook. If you're unfamiliar with the internals of logic gates, see Appendix C for an overview. Note that the CMOS on and off states in the figures are taken from the appendix. Note that upon reset, all ports have a value of FFH in their tri-state registers. This means all ports are configured as an input, which we will see next. Okay, so again, you have to define to the microcontroller what ports are inputs and what ports are outputs. You can see in the diagrams here, these are actually figure 4.3 and 4.4 in your textbook. Outputting, writing a 0 to a pin on the PIC 18, and outputting, writing a 1 to a pin on the output. So in the first case, we're writing a 0. If you go back and review your digital logic, you can see here we've got a latch, a data latch, and a tri-state latch, and depending on the inputs, 0 at a port, 0 at a tri-state, we will end up over here getting a 0 at the output. Same thing applies here. We've applied a data bus 1 to the latch, the tri-state latch, then the series of gates, the logic gates, then will determine that we do in fact get a 1 at the output. So take some time and look at those diagrams, refamiliarize yourself with some of your data logic, and prove to yourself that these do actually result in a 0 or a 1 at the pin. So keep this in mind as you are doing any of your programming of the PIC 18. So the next thing we're going to look at in the next video is the tri-state register role then of inputting data into the microcontroller.